So basically, what is so I'll just have like one very simple slide here, just so we are all on the same page what we're going to talk about. So basically, quantization here it's a process of reducing precision of the model. So basically, here we have this like a Gaussian like curve, which shows us like all possible values that the weights in a neural network can take. And they have like there's like a high granularity here, so they can take like all of the values that are represented in the floating point format and the precision that's used. And then through the process of quantization, we are trying to map these continuous values here into these discrete representations. Basically, we're trying to put all of these like values here in buckets. In these buckets, during this process of mapping them, there will be cases where two values on this these two purple dots will be very close to each other. And because of the quantization process, we have to put them in the fixed buckets. There will be cases where they will be mapped to a single, like to the same number. And this means that during this process of quantization, we will be introducing some quantization error, and the entire game around the quantization is now to is focused around reducing this error so that we can retain the accuracy and the original precision of the model that we are working with. What quantization means in practice? So basically, we are taking the standard data types which are used to represent the weights in a neural network, like FP32, BF16, or FP16. Most likely these days we will be dealing with BF16, which became a standard for modern LLMs. And what we'll be trying to do, we'll be trying to map, this is the possible range of values in BF16. What we'll be trying to do, we'll be trying to map this into, for example, this smaller range here, which is represented with the 8-bit integer values. So the entire game here is around finding the proper scales to downscale this huge range here into this smaller range here. Here I just wanted to lay out some like kind of motivational points on why do we want to care about quantization in general. So basically, kind of, and the most obvious one is that by doing quantization, we're going to reduce size of the model. So we can deploy the model either on a less GPUs or cheaper GPUs. And some kind of like a napkin math that you should be always able to do to figure out which gains to expect from quantization could look something like this. Basically, let's say we start with a Llama 3.1 405B model. The original model has been trained in the BrainFloat 16 format, which means that each weight in this model is represented by 16 bits. So the memory requirements to deploy such model are 810 gigabytes. So we just take 405 billion weights, multiply by 2 bytes, and we get 810 gigabytes. If we were to deploy this model in practice, we would need, for example, on A100 or H100 GPUs, we would need at least 11 GPUs to fit this model. And this basically means that we need at least 2 nodes to serve the model. And what's the problem here? The problem with serving a model across 2 nodes is the fact that we have to pay for 2 nodes now, so it's doubling our cost on one hand, and on the other hand, the entire inference runtime will have a penalty due to this communication that we have to establish between 2 nodes while doing the forward pass, which is going to be significantly higher than the communication that we would experience when just like working inside a single node on like a GPU to GPU communication. So as a solution for this, we can try to quantize the model to, let's say, 8-bit precision. So this means that we are reducing memory of 1 parameter to 1 byte. And now we need 405 gigabytes to serve the model, which means that now we need at least six GPUs to fit the model, and this can easily fit on a single server. So this is just some like very basic kind of napkin math that you can do just to estimate the how many GPUs and which GPUs do you actually need. One additional thing on top of this that's very important to mention is that we need additional space in addition to serving just the model. We need additional space to store the KV cache. during the text generation, but that's kind of a topic for another time. So how quantization improves the inference performance? So basically, it enables us to have faster forward passes through the model. And there are two ways in which quantization is doing this. The first one is by enabling us to have faster loading of weights. So by quantizing some weights, we actually have less bits to move around. And as you will see later on, this is going to be very important bottleneck that we'll have to fight with in a specific deployment scenario. And the other pathway is through enabling the faster matrix multiplications by using lower precision matmals. And this will be also like very useful in one specific setup for the deployment, which we will cover later. And the additional kind of interesting piece of information that I wanted to add here is basically the fact that the deployment of quantized models is steadily increasing. So last year, at the beginning of last year, so now I'm pulling the data from the VLLM. VLLM is one of the most performant and most used inference engines these days. It became like a industry standard for serving LLMs. And basically, at the beginning of last year, there was only about 20% of the models which are being deployed in VLM in some quantization format, and now it's getting much closer to 40%. And this is, I tried kind of to pull out some data here about this, so you don't need to read this. These are just like different colors represent different quantization schemes that people are deploying. And as you can see here, from the March last year to February this year, this is steadily increasing. So where does quantization fit inside an LLM? So basically here, we have this like a block representation of the standard, like a llama for causal LLM class from the Hugging Face transformers. So basically, we see that it's kind of the standard structure that we got used to it. Like we have the embeddings at the input side, then we have n identical transformer blocks, and then we have some norm layer and the final LM head. If we zoom in inside the single transformer layer, we get this structure here. So here we have layer norm layers, which usually don't cost that much and can be implemented very efficiently or fused. But here we have the kind of the interesting part for us are these matrices which happen in the self-attention part and the MLP part. In the self-attention part, we have 4 different linear operators like Q projection, K projection, V projection, and output projection. And in the MLP part, we have gate projection, up projection, down projection. So these are all linear operators, which are like, if we are like talking about PyTorch, implemented as Torch and linear classes, and they're gonna be the interesting part that we want to focus on. And the reason why we want to focus on these specific layers is that if we take, for example, Llama 8B, and we do like some forward passes with some random like a dummy data, and we monitor how much time we spend in each operator inside the Llama model. In the BF16 precision, we'll get a graph that looks something like this. And basically here, like all these different things, like and different colors don't matter. So I'm intentionally like dropping the legend here because I just want to like emphasize the fact that this cost here, like this huge green bar, is the cost that we pay in these linear layers. So this is basically the cost of running this is the time that we spend in all linear layers inside an LLM while we're doing the forward pass. And the entire idea here now is that we, if we want to optimize our inference deployment, what we want to do, we want to reduce this green bar here. And we're going to try to achieve that by doing quantization. And for example, here I'm measuring the same thing, but now in the FP8 format. So I quantized all linear layers to 8-bit precision. And now the green bar is like almost 2x smaller, which means that we're going to get close to 2x speed up in our inference deployment. One just kind of like a side note here is that this trade-off here looks like this for like a reasonable input sizes. If we are dealing with very, very long context lengths, like well 100K, like a million, and so on, these crazy values, then this trade-off here is going to change a bit, because then the attention becomes very, very expensive to work with. But for most use cases, this is what we're gonna deal with. And the main takeaway from this is that we really want to quantize torch and linear. So every single instance of the torch and linear, so the linear operators that we have inside the model, we would like to quantize them. So now that we know what we have to quantize, now let's see which options do we have. So how this linear layer actually works in practice when we look at the memory hierarchy during a forward pass. So basically, at the bottom of the pyramid, we have CPU memory. This is the main memory, usually, let's say 1 terabytes, 2 terabytes that we have on our server. And the main characteristics for this memory are that it's very large memory, but it's also very, very slow. On top of that, we have our GPUs, and they have a high bandwidth memory, something like HBM. This is what you see when you run NVIDIA SMI on your server. So it's going to be maybe 40 gigs, 80 gigs, 24 gigs, depending on which GPU do you have. And the main characteristics are that this memory is much smaller, but it's also much faster than the CPU memory. And then on the top of the chain, we also have one additional part of the GPU called SRAM and tensor cores. And this is the part of the GPU where we have the smallest amount of memory, but at the same time, it's the fastest memory that we have access to. And here, this is also like a zoomed out view. There are like different kind of parts in between these two, like L2 cache, L1 cache, and so on. But for the purpose of the talk here and kind of motivating the quantization, this is enough to clarify what we're trying to do. So let's say now that we have an LLM and we want to do a forward pass with the model. The order of operations that we're going to do is going to look something like this. So the first step will be loading the model from the CPU memory into the GPU memory. This is something that we do only once. So this is not that important to optimize unless we have like some specific set of applications where this loading becomes a problem. But in most use cases, this is fine. Like we pay the cost once and then we have the model in GPU. The next thing that's going to happen while we're doing the forward pass is that we have to load the linear operators, the linear layers from our model from HBM inside SRAM and tensor cores, because the actual computation happens in tensor cores. So we have to take a linear layer, we have to chunk it in tiles, and send it over to tensor cores to do the actual computation. So we need to load the torch and linear, and this is something that we're going to do n times, like for every single linear operator in the network, and we're going to do it multiple times if we're doing like a continuously generating some tokens from the model. And after loading that, we have also to do the computation, which happens in this small part here in tensor cores. So we have to take this linear operator, chunk it into smaller tiles, and do the computation to produce the output for the next layer. So we have these two basic operations, which are going to repeat many, many times during inference: computation and loading of the weights. So basically, because these two are going to be the main kind of costly pieces of our inference, these are the two that we actually want to accelerate with quantization. So the first question here that we're going to try to answer is, how do we accelerate loading? So this first part of the pipeline. So basically, there is no way for us to do anything on the hardware side. So there's like all GPUs come with predefined like a transfer speed between HBM and SRAM and tensor cores. So we cannot do anything there. The only thing that we can do is reduce the amount of data that we need to move around, and that means that we would like to reduce the number of bits of our weights. Because we are loading only weights, that means that we only need to do the weight quantization in order to optimize for this specific bottleneck here on the loading part. The second bottleneck that we discussed is this like a computation part, which happens in tensor cores. Because it happens in tensor cores, all tensor cores also come with predefined number of flops that they can run on. So we need to get a way to like have more flops in our tensor cores. And this is, for example, I'm just putting here like a technical specifications of H100 GPU, just to give you some context. And most of the time, we'll like with unquantized models these days, we'll be operating in BrainFloat 16, and BrainFloat 16 tensor cores have close to 2,000 teraflops. So this is how powerful our tensor cores are. One interesting piece that we can see here is that H100 comes with two additional tensor cores, which have more teraflops than BF16, and those are int8 tensor cores and FP8 tensor cores. And as you can see, both of these provide almost 2x more flops than the corresponding BrainFloat 16. So the solution for us, in order kind of to make the GPU to use these lower precision tensor cores, is going to be quantizing both weights and activations. So the computation that's happening inside tensor cores is like a matrix multiplication between input activations and the weight matrix. And in order to kind of to trigger usage of these lower precision tensor cores, we need to quantize both operands there, and this is called weight and activation quantization. So these are going to be two main formats that we'll try to focus on during this talk and see which one applies to which deployment scenario. Yeah, this is also one note. FP8 tensor cores are like a relatively new thing. So these tensor cores are not available on older GPUs. So basically, they are available on a Hopper and Ada Lovelace and like newer architectures like Blackwell. So for example, if you're deploying LLMs on H100s, L40s, or like these more recent like Blackwell devices, you will be able to leverage FP8 tensor cores. If you're deploying LLMs on older devices, like for example Ampere, like A100 or anything older than that, you will have access only to int8 tensor cores. That's why we'll be focusing on both of these. For the case of weight and activation quantization, we'll be looking at both FP8 and int8, so you get the coverage of more recent GPUs and the older GPUs. So now let's take a look at this like a simple quantization cheat sheet, which should basically mimic how you should think about quantization and in which order you should ask some questions in order to get to the optimal setup for your deployment. So basically, let's say we have a llama model here, which we would like to serve for a specific application. The first question that we should ask ourselves is whether we are optimizing for latency or for throughput. When we say that we are optimizing for latency, this means that we are serving a model, and the main interest for us is to get back to the user as quickly as possible. So a good example for this would be a chatbot application, for example, where we have a user which we just want to wait like 10 minutes to get the reply. So we just want to get back with the tokens to user as quickly as possible. And the second scenario, the throughput scenario, is a scenario where we want to process as much data as possible in the shortest amount of time. So here you could imagine, let's say we have many different documents that we would like to summarize. And we don't care about how much time it takes. We just want to process them as quickly as possible. So we want to chunk them together in the largest possible batches that we can fit in our model, and then to iterate such that the GPU utilization is very high. So if our application is latency sensitive, so we want to optimize for latency, this means that we are in a setting where the benefits the most benefits are going to come from weight-only quantization. So weight-only quantization, this comes from the fact that when we are dealing with this latency-sensitive setup, the main bottleneck that we'll be experiencing and working with is the memory bandwidth bottleneck. So basically, this means that out of these two different parts that we want to optimize, because the inputs are very small, so we have a chatbot and we have only one user who is kind of interacting with the model, the inputs to the model are going to be very small. If it's a one user, so it's going to be just one vector going through the LLM. And the main cost that we'll be paying during this inference here will be the cost of moving the data around. So basically the cost of loading the weights from HBM to tensor cores, and then the computation in the tensor cores will be almost for free. So the time that we spend during the computation in tensor cores will be negligible relative to the time that we need to spend on loading the weights. That's why in this scenario, we don't have any benefits from using the lower precision tensor cores because the computation is kind of for free. So the only way to get the inference speedups is to optimize our model by doing the weight-only quantization to reduce the amount of data that we need to read. Then the second question, the second question that we need to ask ourselves is which hardware do we have at our disposal? If we have Hopper, Ampere, or older devices, what we'll be looking at mostly is integer weight-only quantization to 8-bit weights or 4-bit weights. So here, this representation is a way to say that weights are quantized to 8 bits and activations are kept in the full precision, like 16 bits. Here we are dropping to 4 bits, and then here I have also this block which depicts like a weight-only quantization formats which quantize weights in less than 4 bits, and it's mostly in red because the accuracy impact from doing these very low bit width representations is quite large, and most of the time users won't be comfortable with that, at least based on the existing techniques that we have for quantization. And then if the hardware that we have is like a Blackwell, so like more recent GPUs that NVIDIA is going to release this year, we'll still be able to do the integer weight-only quantization, but we'll also have two additional options to do FP6 and FP4 weight quantization, like two additional formats. And the main difference here is that instead of integers, we can use floating points to represent the weights. The second path here is the throughput. So basically, this is, as I mentioned before, this is the scenario where we want to process as much data as possible. So we have large batch sizes, so we want to crunch to the numbers as quickly as possible, or we just have like an application where we have a lot of queries per second that are coming to our model. This means that in this setup, we'll be bounded by the compute. So because the inputs now are going to be large, the cost to load the weights is going to be negligible relative to the cost that we pay to do the actual computation inside tensor cores. And in this way, as we mentioned before, the only way kind of to get the speed up is by doing weight and activation quantization, such that we can use lower precision tensor cores, which offer like much more teraflops relative to the BF16 tensor cores. And in this setup, then we are doing weight and activation quantization. And the next question here again is which hardware do we have? If we have access to Hopper or Ada Lovelace, like H100s, L40s, we would like to go with FP8 quantization of weights and activations. If we have Ampere and older devices, we have to kind of settle with int8 quantization of weight and activations. And you will see here on Hopper and Ada Lovelace, we can also do int8 because we have support for FP8 and int8 tensor cores. But we want to prefer FP8, and we will see later on, this is mostly because quantizing activations into 8-bit integers is extremely hard because of the outliers in LLMs. We'll touch upon this a little bit later when we get to some results. And then if you have access to Blackwell architecture, then there is additional possibility to get even faster tensor cores. So they're going to be shipped with support for FP4 tensor cores, which means that we can quantize weights and activations to 4-bit floating points and get 2 times more flops than with FP8 and int8. So this all sounds great. Like we have seen that what we have to do and how do we do it. But now let's see how do we actually quantize some actual LLMs to achieve these inference efficiencies. So here I just want to kind of introduce you to the LLM compressor. LLM compressor is, if we have a question. Why W8 A16 means only weight quantization, whereas W88 means both? So basically, this is a standard that people are using, and A16 means that we just use 16 bits for activations. And this means like that's the default bit width that's usually obtained during, like kind of imposed during the pre-training stage. And A8 means that we are quantizing activations as well.
Also, if I can jump into another question, because I think maybe I didn't hear it, but I didn't know this until very recently. Could you maybe just say a few words onto why BF16 is like the standard for LLMs? Because there's these two, there's FP16 and BF16. So what's the difference and why does BF16 come out?
Yeah. Basically, the first data type that we started with, I guess, like a while ago, was like FP32, and that's like the full precision format. And then at some point we figured out that like that's costly to train, and we could reduce this to like FP16 without like having huge impact on the accuracy. And then kind of community moved to FP16, and we use FP16 to train a lot of these computer vision models like YOLOs, ResNets, and so on, until LLMs like arrived. And usually LLMs created this like a problem where a lot of activations have extremely large values, which usually could cause overflow in FP16. So they're like that large that they are exceeding the dynamic range of FP16. And then basically Google came out with the brain float 16 format, which gives us the dynamic range of FP32. So we can represent the same numbers that we could, at least with respect to the range, as FP32, but now we have less precision. So the steps, for example, if you take two numbers, like two integers, like 7 times 8. In FP16, you're going to get the correct number, but in BrainFlow 16, you might be off by a few numbers, because we don't have the same precision anymore. And turns out this has been like a really good approximation, because to train these models, we don't need that high granularity on the precision side. We just need to be able to fit like these very large values that occur during the training. Yeah, if there are no more questions, let's get back to the quantization part. So basically, here, like I'm going to try to introduce quickly the LLM compressor. This is a library that we have developed as part of the VLM project, which should enable to relatively easily apply quantization on top of any LLM that you have. In addition to quantization, it also supports pruning. And one thing that I like to say, that the library is built like for both like practitioners and researchers. And what I mean by this is that for practitioners, so if you don't want to get inside all the details around quantization, all the knobs that you have to tweak to get the proper model, you can leverage all of the existing heavily optimized defaults for all these popular quantization formats. So you don't have to care about that. You just apply whatever the defaults are, and you'll most likely get a very, very accurate model. Whereas for researchers, we also offer a different kind of pathway to quantize the model, where we provide much more granularity over tuning specific knobs, so you can play with many different things which are relevant for the quantization pipeline, both for weight and activations. Like you can play with different quantization scales per channel, per tensor, per group, symmetric, asymmetric quantization with or without calibration data. You can use additional tricks like activation reordering, dynamic, static activation quantization. So there's many different things that you can play with if you want to do that. And then the final piece is that these models that you produce with LLM compressor are going to be saved into the compressed tensors format. So this is an extension on top of the safe tensors format, which has been the default format these days for LLMs, which is basically offers all the advantages of the safe tensors, but on top of that adds this additional step where it's going to apply the optimal compression for your model, so that you get some savings on the disk size, but also it's going to prepare your model to be loaded in VLLM in a way that's going to use the most efficient kernels that exist inside the VLLM. So it's tightly coupled with the LLM. VLLM, if you're using VLLM as the inference engine, then LLM compressor is going to provide you with the heavily optimized checkpoints for that deployment. So let's see at the example here. So I just add like a couple of Python examples just to show you how easy it is to actually apply these optimized configurations for quantization. The script shows how to do the FP8 weight and activation quantization. So basically, you just load your model as any other Hugging Face model, like auto model for causal LLM. From pre-trained, you provide the model stub and you load the model, and then you instantiate a recipe. Basically, in the recipe, you just have to specify what you're quantizing and how. Here we say we just want to quantize all linear layers. As we motivated before, these are the layers that we want to optimize. And then we specify the scheme, in this case, FPA dynamic scheme. And then we call one-shot method. We provide the model, we provide the recipe, and that's it. The LLM compressor is going to do the rest. And then we can just call .save pre-trained, and it's going to be saved in this compressed answers format, where you get the checkpoint, which is heavily optimized for the VLM deployment. The main thing here that you probably haven't seen before and that I haven't mentioned is this dynamic part. So basically, when we are doing this is something specific to quantization of activations. So when we're quantizing weights, there are no moving pieces, right? Weights are fixed, so we can calculate the scales for weights without having access to any calibration data for most of the quantization methods because they're not going to change, right? Whereas with activations, unless we take some data and pass it through the model to see how the activations change, we don't have any way to estimate the range of values that are going to happen inside activations. So basically, all of these techniques, which are doing weight and activation quantization, usually rely on some set of the calibration data. This is like some small subset of the text that we pass through our model so that we can record like some specific characteristics of the activations such that we can compute the proper scales. And in this context of the activation quantization, we have two choices. First choice is to do the static activation quantization, which means that we want to pre-compute these scales like offline and then have them fixed during the inference time. This means that we will take the calibration data, pass it through the model, and based on that, we will estimate the ranges, compute the quantization scales, and we're going to have them as fixed, and then we're going to deploy the model. Whereas with the dynamic activation quantization, what we're going to do, we will compute these values on the fly during actual inference. This, of course, dynamic approach is more accurate because for every single token, we'll be able to estimate the proper scales for the activations. But unfortunately, comes, of course, with some small penalty on the inference side, which luckily for us has been heavily optimized in VLM, and it's usually up to 5% relative to the static one. So it's a really nice trade-off here. So here. We have an example of how to do int8 weight and activation quantization, and it's basically the same story as before. We load the model in the same way that we load any other Hugging Face model. And here, as I mentioned before, because now we'll be doing static activation quantization, we have to provide some calibration data set, and we already have one prepared in Hugging Face Hub, which we can just download and use. And this part here just prepares the calibration data. And it passes it to the tokenizer. And then we have to create our quantization recipe. And one cool part about the LLM compressor is that you can compose different quantization techniques relatively easy. Here we are like composing two different quantization techniques. The first one is smooth quant, and the second one is the quantization modifier, which is our predefined quantization scheme for integer weight and activation quantization, which in the background will use like a one form of the GPTQ algorithm to compress the model. And here we can just kind of put them in the same list, and the LLM compressor will figure out how to run them together. And smoothcon here, just kind of for the sake of completeness, like this is the algorithm that has been developed specifically for like when we're quantizing activations and weights together to tackle this problem that I mentioned before with outliers, because outliers in the activations have these like extremely large values, which are like so like some channels have order of magnitude larger values than values in some other channels, and basically what smooth quant is trying to do is trying to kind of move hardness of the activation quantization to weights, to kind of distribute this hardness to weights, to make activations a bit easier to quantize, and to make the weights a little bit harder to quantize, because usually on average weights are relatively easy to quantize. And then we just combine them, and then we have additional ability here to specify if we want to ignore some specific layers in the model, and then we call the one-shot. We give it a model, a recipe, and the calibration data set, and it's gonna do the rest. If we want now to change the script to do int for weight only quantization, for example, which is like the third format that we discussed so far, it's super easy to do this. Yeah, there is a question.
Yeah, I was wondering, how does this recipe kind of works? So when does it choose, and how does it choose between smooth and the other quantization scheme that you have selected here?
So here, for example, in this, let me go back. In this case here, intake, weight, and activation quantization, we have predefined, like as I mentioned, we have these heavily optimized defaults. So it's going to use like the version of GPTQ that we have optimized for this specific scenario. So you don't have to take take care about like different hyperparameters that are going to like occur in the standard GPTQ. So all of these formats have like some predefined like algorithms which they use behind the scenes, but then you can also tweak and play with them. So for example, here, if you don't want this, you can like add a smooth quant, and then you can instantiate AWQ or GPTQ or any other algorithm that is implemented. Yeah.
Thanks.
Eldar, there was also just one question in the chat. So Arun asked, even if latency is the bottleneck, wouldn't weight 8 activation 8 quantization speed up inference? And doesn't it make sense to apply quantization to both weights and activations whenever possible?
Yeah, that's a really good question. So basically, if we are in this latency sensitive scenario and we do intake quantization of weights and activations, we will see some benefits. So but the benefits that we'll see there are the benefits coming only from weight only quantization, given that in this format we have quantized weights to 8 bits. So now instead of moving 16 bits, we're going to be moving 8 bits. So we're going to have definitely some speed up. But the unfortunate scenario is that we have quantized activations as well, which is going to have like a noticeable impact on the accuracy of the model, but it will not give us any benefits on the inference side. So we will most likely not get any speed ups on the inference, but we will pay the price through the a lower accuracy of the model. That's why we have to be careful when we're quantizing what, which is going to depend on our use case. Are there any other questions? Okay. So, where I was, int for quantization. So if we want to transform this recipe going from intake, weight, and activation quantization to int for weight only quantization, so now we want to target this latency sensitive scenario, like we just drop the smooth quant. It's literally the same recipe. We just drop smooth quant because smooth quant is like for activation quantization, and we change the scheme to int for weights and 16-bit activations, and that's literally it. It's the same recipe. It's just going to run and produce a high quality model for us. And this was the pathway that I described as like a pathway for practitioners and people who actually don't want to deal with like all these details when quantizing the models. They just want to get like a good default and good initial model by just like running whatever there is. In case you're a researcher or advanced practitioner, you want to play a bit with these knobs, and then you want to specify different parts of the quantization pipeline according to your needs. There's basically a way to specify recipes in a more verbose format where you actually can control many different things, both for weights and activations, like number of bits, the type, strategy for quantization, whether you are calculating these quantization scales for the single, like for the entire tensor, for the full matrix, or just like you want to calculate one scale for each row of the weight matrix, or you want to calculate one scale per group. If you're doing per group, then you can specify the group size. Then we have some additional tricks, where you can do some form of activation reordering to fight with this problem with outliers. Then you can do symmetric, asymmetric quantization, and then the same applies for input activations. So basically, there's a lot of moving pieces that you can control if you really want to do that. So now we have seen how to apply quantization on top of our LLMs. Now let's see where the speedups are and how do they look like in practice. So here I'm showing like one set of results from a recent paper titled "Give me BF16 or give me def." So we have many more use cases in the paper, but here I'm just like showcasing the specific one called docstring generation. So basically, what we're looking at here. So we took a Llama 3.18B model. We are serving the model on one A6000 GPU, and we are serving three different formats of the model. We are serving the unquantized BF16 model. We are serving int8 weight and activation quantized model, and int4 weight only quantized model. And then what we're looking at, we are like sending multiple queries per second, like ranging from 1 to 7 in this case, and we are monitoring the inter-token latency. So this is the time spent between generating two consecutive tokens. And what we see here, like this is the BF16, the blue line here. So this is like the baseline, what we would have if we are about to deploy unquantized model. And then if we see that if we pick either the int8 or int4 quantization, we see reduced latency. So we see like a noticeable gains in the speed up here. But there is this interesting point here where the trade-offs actually change, and your optimal choice changes as well. This is related to this memory bandwidth and the compute bound that I mentioned before regimes. So basically, if we are serving a model, and we can put here like the mark at 4 queries per second. So we are serving a model and we have only a few queries, like 1, 2, 3 queries coming. So we don't have enough, large enough inputs to saturate the tensor cores with computations. So our inputs are very small. This means, as I mentioned before, in this case, computation is free, but the loading of the weights is the cost that we are paying with. And basically, the way to optimize for that, as I mentioned before, is to do weight-only quantization. So we have less bits to move around. And then here someone asked before, what happens if we do int8 weight and activation quantization in the latency sensitive use case? You can see that even in this setup, we actually see some gains, right? It's just that now we have this unnecessary quantization of activations, which is not bringing us noticeable gains. And then at around 4 queries per second, when we have 5 or more, what happens is that int8 weight and activation quantization become the optimal choice for our deployment, because now the inputs that are coming to our model are large enough to keep the GPUs at tensor cores busy doing matrix multiplications. And in this case, we are entering this second regime, like a compute bound regime, where majority of the time will be spent in tensor cores doing matrix multiplications, and the cost of loading the weights will be negligible relative to that. And as you can see here, like this is gonna have now as we increase the batch size, it's like the benefits are just gonna be consistent relative to the BF16 model. And then one also interesting thing here is this fact here, like as soon as we cross this boundary, and we start increasing the batch size, the latency of our int4 model will very soon become latency of the BF16 model, because right now we have like large inputs, and the majority of the time is spent during computation. Loading of the weights is negligible, and therefore we actually don't have any benefits from doing the weight only quantization, because now loading of the weights is completely for free relative to the cost of the computation. I think there was a question, right?
Yeah, there's two. So I guess the first one, it's asking wouldn't there be cool if there was an auto-tuner of sorts that could try out these different algorithms and different granularities that you can get with the LLM compressor, and then sort of get the algorithm to choose the best? I guess this paper is giving it to you from an experimental point of view, but is there any sort of technique that does this automatically?
Yeah, unfortunately, this is not yet automated. We did try, in this paper, we actually did some sort of manual investigation for this, mostly because we haven't seen one consistent set of defaults which work best across different use cases. And that's why we kind of have to like kind of manually tune these knobs depending on the deployment scenario. So yeah, we are not, at least we still don't have the quantization algorithms which are going to be like a golden bullet for all problems.
And then the next question is, what effects does quantization have from a more theoretical perspective? So of course, this has a lot of implications for hardware and for the engineering side of things, but is there any benefits, and how would this affect your training dynamics, for example, or any other theoretical impacts that it may have?
Yeah, so basically, yeah, there's one point to make here. The quantization that we are talking about today is post-training quantization. So this is the quantization that we do after we train the model. So first we do the training, pre-training, fine-tuning, RLHF, all these like fancy tricks. And once you arrive at the final model, we take that model and we apply quantization in one shot. There is a different way to apply quantization. This is called like a quantization-aware training. And this is a much harder thing to do. So this means that during the training phase, we are going to simulate quantization. Like we have these like a fake quantizers to simulate the weights are quantized so that the gradient updates can compensate for that. But doing that is extremely hard with LLM specifically, because now we have to replicate the full training process. That means that you have to have like, and GPUs to train the model. And then you have to have the data set for training, which is not going to destroy the knowledge learned during the pre-training phase. So it has like a lot of like these additional complications, whereas the post-training quantization that we are dealing with here today usually fits on a single GPU. So you can run this like a relatively easily for any model that you have.
And then final question that's in the chat at the moment is, does hardware support 4 bits, and how are 4-bit weights stored?
So 4-bit weights are stored in 4 bits. So like the storage format is fine. The main problem with 4 bits is that we don't have tensor cores which support doing operations in 4 bits. So for example, what happens in the int4 weight-only quantization, what's basically happening here is that we have a 4-bit weights, which are stored as 4 bits. We load them as 4-bit weights, kind of to get this optimization of the loading. But then the actual computation happens in the BF16. So these actually int4 weights are unquantized before the actual computation inside tensor cores, because there is no way to do the multiplication between 4-bit operands in tensor cores. That's why we just kind of unquantize them, do the operation, and move to the next layer. And that's basically kind of going back to this memory bandwidth bound. Computation is free, so we can do more or less anything that we want there. The main kind of benefit comes from this faster loading, because now we have less bits to load. And yeah, these Blackwell GPUs will have now support for this. Yeah, like FP4, there will be FP4 tensor cores, which will be able to do matrix multiplications between 2 operands, which are both in FP4. Yeah, that's going to be the next cool thing that will be focused on this year. Yeah, that's the graph. Going back to this, and yeah, if in case you would like to produce a graph like this or similar ones for your own scenarios, we have a library which is going to do this more or less automatically for you. It's called Guide LLM. It will soon, now it's under Neural Magic repository, but it will soon become part of the VLM project. And basically, you can just specify your model, specify the desired quantization format, and it's going to run this kind of benchmarking for you automatically, so you can figure out where the trade-offs are and figure out what's the optimal quantization scheme for your deployment. So
just a query, is there any benchmark to measure the time to first token here?
Yes, you can check the paper. So I intentionally like skipped this part. So there are like these 2 pieces, like which are the most important pieces that we want to optimize: time to first token and this inter-token latency. Time to first token, you can, if you want some numbers here, you can go to this paper, because there we analyze both of these. And the Guide LLM will also provide the details for both, like time to first token and the inter-token. I just kind of focus on this one for the purpose of the talk.
Cool, thanks.
Yeah, so as all other like good things, there always has to be a price that we have to pay. So given that we now are able to apply quantization, we can get speed ups from quantized models, but there is no free lunch. Like we have to pay the price somehow. And the price that we're paying here is actually accuracy. So when we're quantizing the models, as I mentioned before, we are like putting some of these weights which were different, had different values in FP16 format. We are now putting them in the same bucket in the, for example, in Tate format, which means that we are introducing some quantization error. And now the entire game is how do we preserve accuracy under such scenario. And here, I'm going to go through some of the results again from the same paper, where we took a Llama 3.1 model. And the main motivation behind this model was the fact that it comes in different sizes. So from 8B to 405B. So we can see how these trade-offs change across different model sizes. So we have 8B, 70B, 405B. And then we focused on 3 different quantization formats that we also discussed today: FP8 weight and activation quantization, int8 weight and activation, and int4 weight only quantization formats. And the first benchmark that we looked at, so all of these are obtained with these defaults, heavily optimized defaults that we have open sourced through LLM compressor. And that was kind of the main motivation for this work, to find an optimal set of these knobs that you don't have to tweak anymore. The first set of benchmarks is the standard set like of Open LLM Leaderboard V1, like some simple tasks like MMLU, ARC challenge, GSM 8K, HalaSwag, Pino Grande, and Truthful QA in the like different few shot regimes. And we can look at the recoveries here. This is the most important column, and we can see that all quantization formats across all model sizes recover at least 98% accuracy of the unquantized model. And kind of most important piece of the information here is that, as you will see later on through different benchmarks, the hardest one to quantize is always the smallest model in int4 weight-only quantization. This is the one that has been the most challenging one. And as you can see here, it drops to 98.7, whereas the other ones are all above 99% accuracy recovery. The second set of benchmarks are like, again, the same set of models, the same set of quantization formats, but now we look at slightly harder tasks. So this is the OpenLLM Leaderboard V2, like consisting of instruction following, eval, big bench hard, math, GPQA, MUSR, and MMU Pro. So slightly harder benchmarks than the ones in V1. And basically, we see more or less similar story. Like FP8 is usually lossless. It's like 99 point something almost always. int8 is like very competitive to FP8, except for some specific models which have extremely large outliers. One such model is the Llama 70B. So these outliers like are an artifact of the training process. No one knows why they happen. Like there are some speculations, but we are still not sure. And then whenever we want to quantize activations to int8, we have a problem like recovering 100% accuracy only because of that. And then the same thing applies to this, like int4 at the smallest size is usually a little bit tricky. So we have like a slightly lower accuracy recovery of 96%, and all other models are more or less fine. And then if we also looked at the real world benchmarks, here we looked at the Arena Hard. This is like a benchmark coming from LLMs. You're probably aware of the chatbot arena, which has become like the pinnacle of all the benchmarks. Whenever there are new models, everyone wants to look at the chatbot arena scores. This is just the automated way. Instead of using humans to make judgments, it's going to use some version of ChatGPT to make the judgments, just so we can automate this process and run it as many times as we want. Then we also look at some coding benchmarks like HumanEval Plus. And then we also look at the ruler benchmark. This is a collection of long context evals, which has like 6 or 7 different tasks where we are testing the models at specific sequence lengths, going from 4K to 128K. And basically, we see more or less the same story, like to avoid repeating myself, like it's usually like FP8 is lossless or very close. All of them are like above 90, 98, 99%, except for the int4 at 8B, which is usually a little bit more tricky and drops to 96, 97. And then at the end, I included, like, because now we have these reasoning benchmarks, which became very popular, like I included the DeepSeek R1 models. So recently we took like DeepSeek team released a full model family of these reasoning models, where they took all these popular llama and Quen models, they applied like their tricks to fine tune them for reasoning. So we applied all of these three quantization techniques that we discussed today on top of these models, and then we evaluated them on these three popular reasoning benchmarks. And now we are just here showing the average score. And again, the same applies. FP8 looks really good. Int8 is usually fine, except for some specific models where there are large outliers and activations. And then usually smallest models have like a little bit larger drop when doing int4 quantization, weight-only quantization. And then in the interest of time, I'll like just briefly kind of skip to the last slide, which I added like 5 minutes before the presentation. I think it's something very important. So basically, whenever we discuss and talk about quantization, we always look at like how well our quantized model recovers accuracy of the unquantized model. And basically, what we do there, that's like a perfect setup, perfect way to evaluate different quantization algorithms, how well we are recovering the accuracy of our baseline model. But when we're dealing with a real world deployment, when we want to like put some of these models in real applications, the interesting question and interesting pathway that you can take here is by looking at the larger quantized model versus smaller unquantized model. What I mean by this is that, for example, let's say we have a setup where we are allowed to serve only like 7B full precision model. If we decide to serve the 7B full precision model, the accuracy that we'll get is, for example, 65.8. But what quantization does, it unlocks this additional pathway where we can take the next larger model in the series of models, quantize it down to like to get to the inference specifications or like constraints that we have. In this case, we take Quen 14B, we quantize it to either int8 or FP4 or FP8. So we cut the bit width by 2x. So we get the model of roughly the same size, which can fit in the deployment scenario for Quen 7B full precision, but we get much better accuracy, just because now we get to leverage the accuracy, like baseline accuracy of the unquantized model. And then even if we drop maybe 1-2 points, like due to quantization, we still end up with a model which has much better accuracy. Yeah, that's the like takeaway for actual real world deployments of LLMs and not the academic ones. And yeah, that's all I had prepared for today.